Hi all, I am Dr. G. Nirmala, working as Assistant Professor in the Department of Chemistry, VNR VJIT. Today we are going to discuss the potable water and its specification and the steps involved in the treatment of potable water. So you can see the two different glasses of water here. One which is muddy and which is crystal clear. So will you drink this water? No, right? Why? What is the reason? Because we will prefer to drink this water but not this, because it may be like having biological impurities, colloidal matter, clay, microorganisms, many. So what should be the specifications to drink the water? So water should be always clear in appearance, and it should be free from microorganisms like bacteria, fungi, protozoa, virus, algae, which are causing the diseases. And the pH should be from 6.5 to 8.5. There should be no color. It should be colorless, and it should not have bad smell, odorless, and it should be free from toxic substances like chromium, arsenic, manganese and all. And organic, it should be also free from organic substances like phenol, benzene, and there should be no turbidity, and it should be pleasant to the taste. Like we should be having all these qualities if the water is potable. So what is meant by potable water? The water which is suitable for drinking is called the potable water. We have some Indian standards which for water which is suitable for drinking. So the color should be always the 5 ppm below, and it can be extended to 50 ppm. The turbidity should be 10 ppm. ppm here indicates parts per million. It can be little extended to 25 ppm, and pH should be 6.5 to 8.5, and it should not be acidic, and it should not be more alkaline, and it can be relaxed to 9.2. So total hardness causing salts should be in the range below 300 ppm, can be extended to 600 ppm. Elemental calcium 75, elemental magnesium 30, and there will be little extension. And the copper 0.05 ppm can be extended to 1.5, iron 0.3 may be extended to 1. Manganese 0.1 ppm may be extended to 0.5, chlorides 250 ppm, and we will not drink the water, salt water. So may be relaxed a little. Sulfates, nitrates, we can see all these things which should be in the limits, and there will be no relaxation for this. And the fluorides content should be like 0.6 to 1.2 ppm. If the limit is below 0.6, water should be also rejected. And what are the steps involved in the water treatment? So if you take that water which we have seen in the first beginning slides, so water which is muddy, how to make it suitable for drinking purpose. So what are the stages involved? So we will get the water from municipality, right? Directly they will not send from the lakes or ponds or rivers. So after these stages they will send to our homes. So what are the stages involved in purifying water which is suitable for drinking purpose? Screening, coagulation and sedimentation, filtration and sterilization. So we can see all the steps involved in. So you can see the water from the lake. So water will be taken, coagulation, sedimentation, filtration, disinfection, then it will be stored in the tanks, then will be distributed to homes. So the first step we have seen is screening. So the raw water will be sent through the screens which are having many number of holes. So all the floated matter will be collected there on the screens. Then the immediate step is coagulation. So the water will be having like mud particles suspended or clay particles. So to remove them, we have to add the coagulants. So these coagulants will form the precipitates because they will trap all these mud or clay particles or suspended particles and they will settle down at the bottom. So we can see what are the common coagulants we are adding here. So alum, so potassium aluminum sulfates. So usually when the water is having the dissolved salts, when we are adding the alum, it will form the aluminum hydroxide. So which is a gelatinous precipitate which will settle down. And the second one we will use is sodium aluminate. So the sodium aluminate will react with water and will produce again aluminum hydroxide, a flock again, so which can precipitate the magnesium salts present in the water. And the copperous or iron sulfate, so this will react again with the dissolved water and produces ferric hydroxide. So again it is a heavy flock which will settle down at the bottom. For proper coagulation of all these things, we have to maintain the alkalinity. So if the alkalinity is not sufficient, we will add little amount of lime to make it alkaline. And whereas sodium aluminate can be worked less than 7 also, but best pH range is 5.5 to 8. So after, what is the main principle involved in this? So the aluminum and iron which are having the positive charge, these larger cations will neutralize the negative charge present on clay. And because of this gravitational force, they will neutralize and settle down at the bottom. And this coagulation is followed by sedimentation. Usually the water will be kept undisturbed for several hours, usually 5 to 6 hours in a deep tank which is having like 5 meters length. And for proper mixing of the coagulants, we can also add these peddlers, so which are continuously rotating for proper mixing of coagulants with the water. So once they will form a sludge or flocculent, so which will be settled down at the bottom because of the force of gravity. Then immediate step after this coagulation and sedimentation is filtration. So that water, top layer of the water will be sent to the filtration tanks. So we can see the two different filtration tanks, slow sand filter and rapid sand filter. Here usually the filtration tank will be having the layers of sand of different size. So fine sand layer, then supported by or followed by coarse and gravel, bigger sized sand particles. It is usually of 30 to 60 centimeters. So when the raw water is fed after the previous steps. So any suspended particles or any colloidal particles or clay which is left over before the previous steps will be sent to this. All will be settled down, and after some time the filtration becomes very slow. Then 2 to 3 centimeters of this fine sand layer will be scraped off and again replaced with the new one. And this can be also done by rapid sand filter. So where we are using the compressed air to make the process faster. So then the last step here in this water treatment is disinfection. So what is meant by disinfection? So killing or removal of the disease causing microorganisms is called as disinfection. So it can be done by boiling. So usually if we boil the water for 10 to 15 minutes, so all the microorganisms will be killed. So then it is safe for use or drinking. So it can be also done by chlorination. So chlorination is nothing but addition of the chlorine and its compound. Usually it can be done with bleaching powder, chlorine or chloramine. So here the first we are using is the bleaching powder. So we cannot directly add whatever the amount we want. Only 1 kg per 1000 kiloliters of water will be mixed and allowed to stand undisturbed for several hours. So what is happen once the bleaching powder is reacting with water, it will produce calcium hydroxide and chlorine. This chlorine, after the addition with water, released, which is producing the hypochlorous acid. This hypochlorous acid is the powerful disinfectant, and it will start inactivating the enzymes of microorganisms. So usually the most of the whatever the human beings or microorganisms, many biological processes are having the enzymatic reactions. Due to the inactivation of enzymes, the microorganisms will be killed. So there are some drawbacks if we introduce the bleaching powder into the water. As we have seen in the previous equations, so it will form the calcium hydroxide, so which is making the water more harder, as it is giving the hardness causing salt to the water. And if we observe, we have to analyze what is the effective chlorine content which is present in this. When this can be estimated by potassium iodide titration. So usually the calcium oxychloride or bleaching powder will deteriorate after the storage. So calculated amount of the bleaching powder should be added, as the excess will give bad taste and smell to the treated water. So second one, we may add the chloramine also. The chloramine can be prepared by mixing 2 to 1 ratio of chlorine and amine. So this chloramine, when added to the water, it will produce again HOCl, which is a powerful disinfectant. So there are many advantages of adding the chloramine. So it will not evaporate easily, and it will not deteriorate like bleaching powder, and more lasting than chlorine alone, and better bactericidal than chlorine, and excess will not produce any irritating odor, and it will give good taste to the treated water. And if we add chlorine gas, so concentrated chlorine solution can be added, or we can send chlorine gas directly to the water which we want to treat. In the acidic pH range 6.5 to 7. So it will form again HCl and HOCl, a powerful germicide, and leads to the inactivation of enzymes. And if we observe, it will be done by using the apparatus called chlorinator. The raw water and concentrated chlorine solution both will be sent to the chlorinator. So which is a vertical tank which is having many number of baffle plates. Because of the proper mixing, the microorganisms will be killed and sterilized water will be coming out. So the factors influencing the efficiency of chlorine at time of contact: in the beginning, the number of microorganisms available for killing are more in number. So by the time passes, it will kill less number of microorganisms as available number is very less. So with increasing the temperature of water, usually the enzymatic reactions will become faster with the temperature. So if we raise the temperature of water, so efficiency of the chlorine is also increasing. So pH value of water, if it is less than 7 or between 5 to 6.5, it will be working efficiently at this pH range. And what are the advantages? It is most ideal disinfectant, effective and economical, and little storage is required, and stable, and it will not deteriorate like on storage, can be used at high or low temperatures, and will not introduce any hardness causing salts or impurities to the treated water. We do have some disadvantages also, because the excess will give unpleasant taste and also smell. And the residual chlorine should be less than 0.2 ppm always, and most effective below 6.5 pH, and less effective in the higher pH values or alkaline conditions. So this efficiency of the chlorine or addition of chlorine to the water can be also explained by breakpoint chlorination. So what is meant by breakpoint chlorination? It is the point at which the chlorine demand has been fully satisfied in terms of chlorine addition to the water, or we can say, in other words, it involves the addition of sufficient amount of chlorine to oxidize organic matter, reducing substances, and free ammonia in raw water, leaving behind the free chlorine or zero residual, which having disinfectant properties to kill the disease producing bacteria. So this can be explained in terms of a graph. So where we can say easily the breakpoint chlorination is the dosage of chlorine where it can be stopped. Okay. So if we see the first zone, so we can see the destruction of chlorine residual by reducing compounds, or you can also say the oxidation of reducing substances. So what is happening here? So most of the chlorine added in this region gets reduced by transition metals like iron, manganese. Okay. So total chlorine residual increases minimally with the addition of free chlorine. So it will start forming the monochloramine, dichloramine, like trichloramine, and all will. So formation of chloroorganic and chloramine compounds will be added. Usually the total chlorine residual increases as more free chlorine dose is added. So more chloramines will be formed. So once you can see this in zone 3. So the total residual chlorine will drop. So all the chloramines which are added will be destructed here. Then after this, once the breakpoint chlorination is reached, the chlorine residual increases roughly or linearly with the addition of free chlorine. So now which is left over once, or this is free residual chlorine, where we should stop adding the chlorine to the water. And we should always see that the residual chlorine should be 0.2 milligrams per liter at the contact period of 10 minutes. So what are the advantages of breakpoint chlorination? So it oxidizes completely all the organic compounds which are present in the water, and also ammonia and even other reducing substances which are present. It will also remove the color. So usually if the water is having color, it may be because of the metals present or organic matter present in it. So it will remove all those things, and it will destroy completely all the disease producing bacteria, and removes bad taste and also smell from the water, and it will also prevent the growth of weeds in the water. So we have seen already the over chlorination or excess of chlorination will give bad taste and bad smell. So how to remove this excess chlorination, chlorine present in the water? So the dechlorination can be done by sending the water through the bed of molecular carbon, so that the excess chlorine can be adsorbed on the molecular carbon bed. Or we can also add small percentage of activated carbon or sulfur oxide or sodium sulfite or sodium thiosulfate here. So this is about the steps involved in the municipal water treatment and what are the specifications of potable water. So we can see the references here. Thank you.